You know, we are constantly in the middle of a hidden battle, a fight for privacy that's happening right now, inside your phone, on your laptop, and all across the internet. Today, we're diving deep into that secret conflict, the cryptographic arms race. Think about it. Every single time you send a text message, buy something online, or even just type in a password, you're relying on this invisible shield to protect your private information. But have you ever wondered how that shield actually works? What's really stopping someone from seeing everything? Well, let's break it down. Okay, so let's start with the big picture. It's called information security. And this is not just about computers and hackers. No, this is the whole shebang. The entire practice of protecting important info in all its forms. We're talking digital files, sure, but also paper documents in a locked filing cabinet, or even just a conversation you whisper to a friend. Now, cybersecurity is the slice of that pie that we're all most familiar with today. It's basically information security for our digital lives, protecting our data, our devices, our networks. And right at the heart of cybersecurity is one of the most powerful tools ever invented, cryptography. And this is our main character for today, cryptography. At its core, it's the art and science of keeping secrets. It's all about finding clever ways to communicate securely, even when you know other people might be listening in. So how does it all work? Well, it really boils down to two fundamental ideas. First, the sender takes their message, we call this the plain text, and they perform encryption. This uses a secret to scramble the message into a totally unreadable form called ciphertext. Then, on the other end, the intended receiver performs decryption, using that very same secret to unscramble the mess and turn it right back into the original message. That secret we keep mentioning, that's called a key. Now, there are a few different kinds, but for our story today, we're going to focus on the simplest type, symmetric key cryptography. It's pretty straightforward. It just means that you use the exact same secret key to both lock the message up and to unlock it again. Both the sender and the receiver have to have a copy of that key. But you know, this whole idea of using a single secret key, it is definitely not new. In fact, to find its origins, we have to go way back to ancient Rome, and to one of the most legendary military commanders in all of history. We are talking, of course, about the Caesar cipher. And the concept behind it is just beautifully simple. You start with your message, you pick a secret number to be your key, and then you just shift every single letter in your message forward in the alphabet by that number. That's it. All right, let's try it out. Let's get our hands dirty. Our message, our plain text, is this is an example. And for our secret key, we're going to choose the number 3. So we're going to shift every letter forward 3 places. Okay, let's start with the very first letter, T. If we count 3 letters forward in the alphabet from T, we get U, V, W. So T becomes W. See? Simple enough. And from here, we just keep going. H becomes K, I becomes L, S becomes V. And you just do that for the entire message, letter by letter. And just like that, our scrambled ciphertext starts to appear. I mean, look at it. It's complete gibberish to anyone who doesn't know our secret key, our secret number, which is 3. And there you have it, the fully encrypted message. Now, for the receiver to read it, they just do the exact opposite. They take each letter and shift it back 3 places, and the original message is revealed. Pretty clever for its time, right? And for a very long time, over 1,000 years in fact, this was a pretty solid way to send a secret message. But of course, the arms race never stops. Codebreakers got smarter, and they started finding some really big flaws. So problem number 1 is what we call a small key space. Think about it. Since there are only 26 letters in the English alphabet, there are only 25 possible numbers you can use for your secret key. An enemy could literally just sit there and try every single one. That's called a brute force attack. And with so few options, cracking this code is actually really easy. But there's an even bigger, more fatal flaw. You see, every language has a sort of fingerprint, and it's based on how often certain letters appear. In English, for example, the letter E is the most common by a long shot. The Caesar cipher doesn't hide this fingerprint, it just shifts it. So if a codebreaker sees that, say, the letter H is the most common letter in your secret message, they can make a really good guess that H is just the encrypted version of E, and boom, they've instantly figured out the key. So the big takeaway here is this. The weakness was using one single, unchanging shift for the entire message. The solution then had to be to find a way to use lots of different changing shifts. And that brings us to the 16th century. And the next huge leap forward in this arms race, the Vigenère cipher. For hundreds of years, this thing was literally nicknamed the indecipherable cipher. And its secret weapon? It's what's known as a polyalphabetic cipher, which is just a fancy way of saying it uses many different shifts instead of just one. Here's the magic behind it. Instead of a single number, your key is now a key word. In this case, let's use the word secret. So the first letter of our message, T, gets shifted by the first letter of the key, S. The second letter, H, gets shifted by E. The third, I, by C, and so on. And if you've run out of letters in your keyword, you just loop back to the beginning and start it over again. Now, why is this so much stronger? Well, think about it. The same letter in your original message can now become different letters in the encrypted text. See here how the letter I becomes a K one time, but an M the next? This completely flattens that language fingerprint we talked about, hiding those patterns and making the code way, way harder to crack. And this constant back and forth between the code makers and the code breakers, that is the cryptographic arms race. It's this incredible evolution that's been going on for thousands of years. From the simple single shift of the Caesar cipher to the multiple changing shifts of Vigenère, all the way to the mind-bogglingly complex algorithms like AES that protect our digital lives today. Which, of course, leaves us with one final big question. This race is far from over. As our computers get exponentially faster, especially with things like quantum computing right around the corner, even today's so-called unbreakable codes will eventually fall. So the question isn't if the next great leap in cryptography will happen, but when, and what the future of our privacy is going to look like when it does.